Welcome back to the shop, folks. Sunday evening here. And after a lot of unrelated stuff this weekend, we're finally ready to get back to that gimbal. But first, some cat. Not that, this. So this is kind of the, I guess, a prototype or a predecessor to the flying Tuco tracking sort of robot that we're going to be making. He does like his carpet squares. So there are a lot of components to this project. The eventual goal is to have this camera, or something similar to it, up on a kind of a robot that flies around on wires, and then have interaction via Twitch chat or whatever else people can think up. So there are many parts to this project. There's the gimbal that actually holds the camera and stabilizes it and lets us aim it. So that's what we'll be focusing on in this stream. There's the robot well, the robot itself you could think of as having multiple parts too, because there's the actual flying part, which isn't that much of a robot. It holds the gimbal, it'll have some sensors and some compute power. But then the actual motors will be managed by these little dudes that I've been calling winch bots, and there'll be 4 of those, one in each corner of the space here. And each of those will have a little microcontroller doing some local motion control. It'll be communicated, all the motor controls will talk to each other and the Raspberry Pi over a dedicated Ethernet network, which will be just motor control. So the idea is that I would use Ethernet a lot like you would use something like RS-485, just to send messages to a bunch of things that are separated by distance. But in this case, Ethernet was pretty easy to use, and with only these devices on the network, it won't be clogged up with unrelated traffic. And I suspect there's going to be some kind of real-time, like actual hard real-time system built over the Ethernet. So I would have the motors expect update packets within a certain rate, and you could imagine basically having a software emergency stop that works by, just cutting the power as soon as you don't get packets from the Raspberry Pi within, 30 milliseconds or 80 milliseconds or something, and then to have something in the other direction so that the Raspberry Pi shuts down the whole system if it doesn't get responses from any of the motor controllers. So that's why for the emergency stop here, I was thinking that I'd have a button on each winch controller, which would just cut off power to that winch controller. But due to this watchdog inherent in the software protocol, you'd also end up shutting down the whole robot that way. And then there could be other kinds of emergency stops elsewhere in the shop, like maybe if I have a wired controller, it would have an emergency stop button. And of course, there's also an e-stop on top of the rack, which would end up working, although it's probably overkill if you just want to shut off the robot. So, many parts to this. There's the winch controller, there's the flying compute thing with sensors and the gimbal. There's the gimbal itself. Let's see, let's take this away so you can see Toog still. So here's the gimbal that we've been working with. So this is the actual gimbal that, assuming we can fix it, is actually going to be flying on this robot. it's been modified on several previous streams so that it's holding this, I don't know how I'd exactly describe this camera, but it's basically a HD closed-circuit TV camera, and it's got a pretty nice lens on it. The main advantage over the GoPro that this is designed to hold is that we can use, excuse me, we can easily stream HD video. Oh, hey. My friend Zach just got back. So the advantage of this camera is that we can easily stream HD video over pretty much an arbitrary distance just using cheap coax cable. So that and the host of other things, the nicer adjustable lens and the night vision, it seemed handy to use this camera. And so some of the modification was making a bracket so that we could mount this camera, and then running a tiny coaxial cable back through each joint in the gimbal to get the video signal out to this connector. And then this thing on the side is a LiDAR, it's a laser rangefinder sensor, and that's going to be used mostly for focus assistance. This doesn't have motorized focus, but I figure we can set a distance range that works for focus and then use this to have the robot move to the appropriate place. So, this was working pretty well. We got it basically working, from a mechanical design perspective. I designed these brackets, shaved down a bunch of parts, bolted it all together, did a bunch of the kind of electronic mods to the gimbal, and so all that actually worked out pretty well. And then we got a little more ambitious, and, well, there was one incomplete piece, really. So even with all the mechanical mods done, we didn't really have a way to control the gimbal like I'd want. The control scheme with the stock firmware happens to be, kind of mapping a joystick to the inputs, and it has a mode where you can map the vertical axis on the joystick to pitch, so it just maps that directly to an angle. But for yaw, side to side, it doesn't have that mode. The best you can get is like a speed, and it's got an absolute, encoder, a magnetic encoder in this joint. So it actually knows what that angle is, but using just the documented, RC servo kind of control protocol, there's no way to do anything with that programmatically as far as I can tell. So my plan there was to get around that by, still controlling it using the joystick interface, but getting my own feedback from that sensor just by tapping into it directly. So we'd have an FPGA, just some programmable logic that we could use to do this fast interfacing if we wanted. That would be stacked onto the Raspberry Pi. And then that whole contraption would be able to both generate kind of fake joystick inputs for the gimbal and spy on its existing yaw axis magnetic sensor to see where it's actually pointed. So that was my plan until something better came along, which was we started looking closer at the protocol that this gimbal uses just for its little kind of dinky Windows software settings app and for the firmware updates. And so the stock gimbal package includes a piece of software and a cable. It's got this port that looks like micro USB, but it's actually 3.3 volt serial, so they give you an adapter and they don't really explain what that's about. It's kind of sketchy, but it works if you plug it in right. And we looked closer at that, and this protocol, it's clearly used for firmware updating. It's clearly used for some of the settings that are exposed in that app that they give you. But you'd assume that that's also something that would expose a bunch of other settings that they don't usually give you direct access to. So my hope was that it wouldn't just be for settings, but there'd also be a way to actually point the gimbal over that serial protocol. And if that was true, then I could kind of get everything I wanted. I could control the gimbal over serial. I could either control or read back its absolute heading on that yaw axis so that I could, I wouldn't have to tap into the magnetic sensor. I could just control it directly. And so this was kind of an investigation. It wasn't really something that was sure at all, but it seemed worth looking at. And so we were looking into it and actually seemed to be making some good progress. The protocol that this gimbal uses to talk to its Windows software turned out to be pretty simple. It has a little header packet with a command type. It has a byte that seems to indicate which microcontroller in the gimbal the command goes to, since this gimbal actually happens to have a separate micro in each joint, which is a pretty interesting architecture. So then, we started developing this theory that maybe the first microcontroller in the chain is just kind of translating the RC servo style pulse width modulation, the 1 to 2 millisecond things that you usually get in an aircraft. Because again, these are designed for quadcopters. I'm totally repurposing it, talking to it with a regular microcontroller. We had this theory that maybe the first microcontroller in this chain here converts those into some other serial protocol and then sends them along. And then after looking at this closer, we thought, okay, this is seeming pretty likely. What if we just snoop in on the traffic that's going between the first microcontroller and the second microcontroller, then run it in regular joystick mode and see what comes out, see what's being translated. And that worked. We actually got, we figured out enough of the protocol to figure out some of the setting mechanisms, so how you load and save settings on the gimbal. I have a pretty good candidate for the command that the pulse width modulation inputs are being converted into. We don't know exactly how it works, but I think we know enough to play with it. And then we started actually playing with this command interface using the serial port connected to the Raspberry Pi, and then actually running Python code on the Raspberry Pi using Jupyter Notebook, and then interacting with that over the web browser. So we could just add sliders on our notebook that would control values in the camera's parameters, or the gimbal's parameter space. So that was seeming pretty cool. And then I messed it up. I made a mistake. Where's Tuco? I don't see the cat, but I'll keep an eye out for him. Yeah, so made a mistake, and I don't exactly know what the form of the mistake was exactly, but somehow I erased or severely corrupted the settings on the gimbal. So it seems to have some non-volatile memory that stores a host of things. So there's some documented stuff, like you can give it a heading adjustment for where the center is. You can give it, you can change the speed that it tracks movement. As you move the gimbal around physically, you can change how fast it points the camera in response, things like that. So it's got a whole memory space where it stores parameters like that, and I messed up something else in there, something we don't have any documentation for. So made some kind of blind attempts to fix it on the last gimbal-related stream, but didn't really get very far. And then something awesome happened, and Mark WHI in chat donated this spare gimbal. So yeah, we were shopping around online, and apparently you can get them even a little cheaper. That I found this one on eBay now, and so this should be the same model. This is the Feiyu Mini 3D, not the Mini 3D Pro. As far as I can tell, the Mini 3D Pro is a little bit different. Just visually, it has an extra aluminum piece around the circuit board. I don't know whether it's going to be different protocol-wise, but it's probably a little bit different mechanically and probably has different motors. But as far as we can tell, this is going to be the same model. So the plan here is to open this up, make sure it works, and then try to carefully use the code that I've got so far to slurp out the parameters and save them, and then try loading those parameters onto this other gimbal to see if we can get it working. There might be some factory calibration that's per gimbal, but I kind of doubt it. I doubt that they would want to spend the production effort on that, but if so, I'm hoping that these are close enough that they still run. So I think that's the plan. I do want to be careful not to repeat the same mistake. So one concern I have is that I don't know exactly how the problem happened. There are a couple of candidates. One of the, so there were a couple of places where, due to some kind of communication bug or a bug in my script, I ended up sending just a long string of zeros or something else that was just kind of malformed. I'm forgetting who was doing this now, but someone in chat had actually noticed maybe the exact moment that the gimbal got its settings corrupted, and it seemed to be related to a buggy program that I ran that just spammed it with a bunch of just oversized packets. So there's a packet that does it wasn't even a set command. So there are commands. There's a command that gets a parameter. There's a command that sets a parameter. This was a really oversized get command, and issued several of those. And right after that, the gimbal just started bouncing against the end stops, and I pulled the power as soon as I could. So I'm not entirely sure what happened there, because I wasn't even issuing commands that I would expect to have any effect right away. I was issuing commands that would just be responding. So my hunch is that maybe I hit a bug in their code, maybe even a buffer overflow, which could be interesting. It could be potentially a way in later. As an aside, we've been trying to see if we can actually just kind of get in the usual kind of front and side doors that you have in a microcontroller system, just to start poking in at a lower level. So far, the reverse engineering has mostly just been by looking for hints in the traffic between it and the Windows machine, and kind of trial and error and experimentation. The Windows software, well, I haven't looked super closely at the Windows software. It didn't seem to do much more than what it actually exposed via the UI, but we haven't really looked closely at the Windows software in disassembly since we got a better idea of what the protocol even looks like, so there might be more hints left to find in there. But so far, most of the hints have just been coming from experimenting with the protocol bit so far. And the interesting stuff, especially like the write and read parameter commands, were barely used in the original software. The Windows software used the read parameter command just to see what the heading follow mode was supposed to be set to in the UI by default, but nothing else. So a lot of this is just kind of entering into undocumented territory. Yeah, as Ktemkin mentions in chat, so hopefully once I find the differences in the configurations, they're structured or closed off enough that I can figure out what the parameters mean and calibrate the device itself. Yeah, that's my hope too. Before I totally corrupted the parameters in this gimbal, my plan was to use one of those Jupyter notebooks with the sliders to interactively just kind of nudge each of the parameters a little bit to try to figure out what it was doing, and to try to and as they're saying, hopefully they're structured enough that we can figure out what they mean using some contextual clues. I think we also figured out just some structural clues about how the gimbal works from the last set of investigations. So there were some questions about how the how the division of labor was done between the different microcontrollers, since it has these 3 different micros, and they're probably all doing slightly different jobs, but they probably also have a common core of functionality just necessary to, I'm imagining that each axis is like its own little 1D PID loop, so it has its own absolute encoder, it has its own motor for output, and then it's running a little algorithm that just does its own little 1D PID loop for that joint. But then there's some global coordination that takes each of those axes and brings them together into a whole system, which could be wrong. It could be entirely done with 3 separate axes, and they each just kind of take part of their workload. But my hunch is that it's a combination of the 2. And so my hunch about this so far is that each axis has its own little motor control snippet, which is largely the same. And from what we've seen, that parameter space is separate for each axis, but largely the same. So each axis has its own, we've seen things in there that are probably like on-offs and gains and positions for the encoders, and those are all laid out the same for each axis. But to read the encoder on a particular axis, you would send a get command to that axis's microcontroller, and then look for the encoder's slot in the parameter dictionary, parameter array there. So I think that's what we're dealing with. But my hunch is that the differences there. I think the microcontroller closest to the quadcopter, which I think this is going to be number 0, if I'm remembering correctly. So they're numbered 0, 1, and 2. Number 3 is used in certain parts of the protocol to refer to whatever's talking to this, so like the Raspberry Pi in this case. I think the way this works is that 0 is responsible for converting the pulse width modulation input into an actual kind of serial command when this is in pulse width modulation mode. And that 2, which is to say the one closest to the camera, I think that one's responsible for reading the accelerometer, the IMU sensor over I2C. So I think that was also going to be the microcontroller that runs the algorithm, the stabilization algorithm, or at least the parts of it that are that are running in all three axes. And I think the way this is going to work is instead of sending back IMU data kind of from camera end to base end, the way this is working is that the microcontroller closest to the camera does all of the kind of higher level calculations itself, and it also is the only one that talks to the actual IMU. But then it sends back a group of packets for the other two axes, telling them some kind of command target. So maybe it's a speed or an angle or a torque or something, some target for its local control loop. And then the local control loop on each joint kind of slurps up those values and then kind of really quickly iterates on reading back its own local sensor values and commanding the motors. So I think that's where we're at so far, just for a bit of a recap. So at this point, I want to boot up the Raspberry Pi, but then mostly just put this gimbal aside and just get the other gimbal started up and extract the parameters carefully without messing up. So we're going to try to just, well, actually, the safest thing to do would be to write an extraction script and then test the exact script I'm using on the gimbal that's already messed up, and then transfer everything to the new gimbal. So maybe that would be the first thing to do. I'll save this box for just a second. Ooh, that is quite the squeak. Oh yeah, just for a slight diversion, there's something else relevant to this. So I may have already mentioned this, but I think I was describing all the different parts of this whole project. One part of it, which I haven't really mentioned that much, is that it'll be streaming, of course. You'll be able to interact with it. I've just recently started experimenting with getting that part set up. So if you go to twitch.tv/TucoFlyer right now, so Tuco is the name of the cat, and TucoFlyer is the name of the robot. And so this will actually just be a separate feed that's just the cat camera. It's still kind of experimental. I might turn it off sometimes if I'm working on it, but I'm trying to see if I can get this set up here ready to have like multiple outgoing streams all the time. This one's going to be lower bitrate for now, but I'll try to point it at the cat every so often. But then the idea is the streaming hardware for this is pretty much identical. It's the same camera, same SDI signal. I would just plug this into a different camera once I have the robot ready. I'm going to point this at Tuco, but I don't see him. Oh, Tuco's in the best spot. So yeah, there aren't any Twitch commands, and this stream is currently silent. It's not going to have shop audio 24/7 because that would just be creepy, but it, I might have some kind of ambient music for it eventually. But right now it's just quiet Tuco. And then just for a quick update on the other parts of this project, I've been doing a little bit of CAD lately off stream. Oh, I should grab my 3D mouse, because then it's much more fun to fly through here with a 3D mouse. Okay, let's exit rendering mode for a sec. The rendering mode is nice, but this is a little more practical. Oh yeah, I highly recommend these 3D mice. I mean, not a lot of programs support them outside of the kind of like big CAD tools, but they're really handy. So just for a high-level view, this is the robot that controls the winch, or rather, this is a winch bot. It is a self-contained one-dimensional CNC machine, basically. So the goal is you'd have 4 of these stationed around the room, roughly in the corners. They would lead up to the ceiling where there's another pulley. These could be pretty much anywhere along the wall. I'd mount them just wherever it's convenient. And I was thinking I'd want options for mounting it either to something vertically like a wall or something horizontally, like probably not the floor here because the floor is cement and I wouldn't have any way of mounting it, but like the top of a heavy object maybe. And the way that this is designed, so you can probably guess that like this is the spool that actually takes up most of the cord. And I've got some pulleys up here that these two basically serve to try to align the cord in the middle of this and to align it into a plane up here and kind of account for that difference. And then the combination of these 3 act to measure the cord's travel using this optical encoder. And then the combination of this pulley and the load cell measures the force on the cord. So we can, it's roughly some force feedback, so we can use that to try to balance the forces among the multiple axes we're dealing with. And you can kind of see how the components pack. You can see a bit more if I actually take the enclosure off. So the enclosure is actually already in multiple pieces. But without any of the enclosure, here's just the insides. So there's the spool, there's a bearing in the middle that it actually runs on. There's a big old gear motor, 24 volts. And the positioning of this motor at a jaunty angle like this is mostly to kind of minimize the envelope size of this whole thing. Because if you imagine if it was pointing out sideways, then I would need kind of an appendage on the side of the enclosure. If it was straight up and down, there wouldn't be as much room for this stuff. Also, having the center of gravity a little further toward the wall mount means that there's less, I wouldn't mind some amount of counterweight pulling down against the cord, but I don't necessarily want this thing when it's idle to be just like a heavy mass on the end of a lever. So keeping the heavy parts close to the wall seemed like a good idea. So motor, there's the motor driver board. Under there is the load cell amplifier. Got an emergency stop, sensors. And so the idea with the enclosure is that there'd be kind of a central core roughly right here where my mouse is vertically. And that would be providing most of the strength. I haven't modeled any of that yet. But if I put the enclosure back on, my expectation is that so there's kind of a strong core there, and that most of this blue part would probably be a solid piece. I might break it up just for ease of printing, but there isn't really a need for any of that to be broken up. And then to access the electronics, this lighter blue cap, which also makes kind of a nice contrasting shape, that would come off. There'd probably be a screw or some clips or something holding that on. And then that gives you access to the microcontroller board here. If you take out the microcontroller board, underneath it you get access to the motor controller and the load cell amplifier. And then if you actually take these 2 halves apart, these will probably come apart with some screws on this side. If you take this cover off, let me just hide that cover. So if you take the cover off, then you'll have access to all the kind of mechanical parts. So if you were taking the cord off or respooling the cord, then you just take this cover off. And so I think that would still work even once this is mounted. Like that could be attached to a wall and you could still take this cover off. I might want to chamfer this edge a little bit if that's the case. And then the way the cord winds, it loops through the middle of knots, and then it goes around this, then over both of these idlers, under this capstan, under this idler, and then straight up. So that's the plan so far. And I think one of the things I'm most unsure about right now is probably the wall mount. Let's see if I can get a closer view here. Yeah, so the goal with this part was partly to use the extra space around the motor gearbox to give some kind of cable routing and strain relief space, and to allow access to the mounting for these two options. These center pads with the ridge around them, the idea is that you'd put the butt of a C-clamp right there, and it would keep the clamp from sliding off. And so these are both for C-clamps. Then these are for if you have bolts that you've like driven into the wall and you want to drive them most of the way in and then slide this on sideways and then tighten them with like a wrench or like a stubby hex wrench or something. So I don't know how well this is going to work. It might be too weak or too hard to mount, or both. This is also totally something where if I needed the reinforcement, I could probably put like a plate of sheet steel or something in here, but I doubt I'm going to need that. I mean, my design strategy here has mostly been keep it relatively light duty and just use kind of big chunky plastic to spread out the forces. So that's kind of what I'm trying to go for here. And then with the cable routing, so on this side you have USB, which likely wouldn't be used for anything in normal operation. I'd probably throw a debug UART or something on there, but maybe not even that. So there'd be a USB port that probably wouldn't really be used. There's a DC power jack, 24 volts at a couple amps probably. There's RJ45 networking. And then on the other side of this circuit board, there's another USB connector for in-circuit debug, and there's a JTAG. I'm not going to have cutouts for those on the enclosure, but if you just take off this blue plastic piece, then you have access to the debug ports. Yeah, Ryan's suggesting maybe consider a separate mounting plate, so I'm assuming like something that you bolt onto the wall first and then you like attach this somehow. Yeah, I was thinking about something like that. I mean, part of what I like about this is that this, I mean, assuming I can get the materials and the print settings and all that such that this, you know, spreads out the force really nicely along that contour, I would expect that this mechanically would do a pretty good job of, because, I mean, I'm trying to think of, so, I don't know, I guess I've been mostly focusing on wall mount since I think most of these are going to be wall mount. So for wall mount, imagine this side is up against a wall. You have, you know, 5 kilograms or so of force vertically here, and then you have, you know, maybe like a kilogram or something down. There isn't really that much total. You're going to have some jerk up and down as things move around. But I guess I'm imagining that mostly this is going to act like a lever. Like imagine the fulcrum is kind of up here somewhere. And so the pull up here is going to want to extract these screws from the wall, which they should be pretty good at not doing. I mean, you might, maybe don't put this on drywall, but I'll be attaching this to either like wooden or steel beams probably. And so these will fit M6 nuts, or like M6 bolts rather. A well-designed future product. Well, you know, a lot of stuff looks good in CAD. This would be, I could go ahead and put this on Kickstarter. But no. This needs a lot more work. I mean, none of the internal features are ready. This is just me trying to get the exterior shape about what I want. All right, well, I think that's enough of that for now. Let's go back to the Raspberry. Okay, so just for a bit of a recap, the setup here that we've been using to poke at the gimbal it's based on this thing called Jupyter Notebooks, spelled with a pi, like Python. Come on. And it's formerly known as IPython Notebooks, if you're familiar with that. And one thing that's nice about this, it already has this nice kind of network transparent UI where you're running the Python code in this one process that you can run on the Raspberry Pi. Then you have this local user interface that will seamlessly talk back and forth over WebSockets. Yeah, CAD program and a video editing program, and you got funding. That's how it works, right? I think we need some power for the Raspberry still. Oh, geez. Maybe I should float the power supply again like I was doing before. So I had what I can only assume is a fairly nasty ground loop issue that was causing my USB hub to reset every time Yeah, I guess that was only when I was doing the USB to serial adapter with the Raspberry Pi. I think I'm going to try to avoid that. Keep the power supply grounded. There we go. Gotta cover the positive 12 volt banana cable with tape or something bad's gonna happen, I know. Okay, so I'm not going to plug in the 12 volts yet. I'm just going to have this handy. There's something else that I meant to change, which maybe we can go back and do. Well, and so we don't have to use IPython for this part, since it'll probably make the most sense just to have a little standalone script that gets the parameters, but I think part of why the stuff that I was doing in IPython before got so messy was I was attempting to do asynchronous kind of callback-based programming for some of the procedures, when really I think I should just embrace blocking programming for that. And, you know, because I have background threads doing the receive and transmit, but I think that the functions which are of the form, you know, like get parameter, like that function itself, I think should actually block on getting the receive with a timeout. So let's try implementing it like that, because we were having problems with like the queues getting desynchronized and, you know, having to write like special purpose wrappers for retrieving lists of things, and it was just getting gross. Robert has a dumb question. No, I don't know if that's a dumb question. That's just what you labeled it as. Do kernels running under Jupyter have a controlling TTY? They would, assuming you're running Jupyter from a TTY, which I think I usually do. Anyway, let's see if we can SSH into the Raspberry here. So this is our Git repo. Let's just bring this up for reference. So if you are brave enough to brick your own gimbal and follow along, I've got this repo with the work so far, this FY gimbal repo in my Git. So far we have a SIGROC decoder for their protocol, some kind of low-level stuff here, an IPython notebook, and a bunch of example traces from the experimentation so far. The .sr files are in SIGROC's compressed raw format, and the texts are already decoded. It's too big for GitHub. All right. Ooh, this mouse is way sticky on the new mat. Does not make a good mouse pad. Okay, and as fun as this environment is for running Python code, I prefer to use a local editor. So what I usually do for that is use SSHFS, which I think is a great program. Some people complain about it, but I like it. And life's too short to complain about everything. Alright, so we got our local text editor of choice. So this is our IPython notebook before, which you can tell is not super useful as a standalone file, but we can open this under IPython, and maybe we'll just go ahead and do that now to have it handy. So for IPython, let's see, so we want to run IPython 3 notebook. And actually, I kind of want to run this in the root directory, and, oh, I kind of want screen. This is just so that if I lose the terminal, then it doesn't end up killing the IPython kernel, because I kind of want this to be persistent for a little bit at least. Yeah, I think Robert in chat has a standing tradition of every time I mount an SSHFS file system to complain about it, which is funny because I don't think it's actually been a problem at all lately. I mean, I've used some buggy file systems in the past. Anyone else remember UnionFS when that was brand new? All right, so we got screen. IPython 3 notebook, not Python. That would be an interesting name. And then I think, since by default I think this binds to only the localhost interface, I think it's got to go page in a bunch of stuff from the SD card. Is that stuck? Huh. That's interesting. My Pi seems to be stuck. That could have been a number of things. I wonder what it actually was. Does an existing connection work? Not so much. All right. Yeah, I think it's stuck. Apparently Robert wants me to try really hard to hate SSHFS. I think I'd rather not. Yeah, okay, I guess my Raspberry just crashed. I don't know what happened. I thought it might have been a power glitch. It's possible I glitched it somehow, but everything looks fine. Let's reboot it. Yeah, my embedded development environment of choice is SSHFS and Sublime Text locally, since Sublime Text also seems to be decent at not like blocking on the disk all the time. I don't know, that's just what I like. Man, I can't even like kill SSH using the escape. I might be forgetting what it is. I like have to escape out of SSH connection so rarely that I think I often forget what the escape code is for killing it. Oh, and we're back. Let's try that again. So, great, so we have screen running now. So one thing that's been nagging at me is I don't actually know if that IP option is necessary, so let's just try IPython 3 without that and see what happens. This is the most straightforward way of starting it. Let's see if it works. Oh, gotcha. Jupyter Notebook is apparently the new hotness. And okay, so it does need to be told what interface to bind to. So if you see this HTTP localhost here, that will only work from the Raspberry Pi. We need to tell it to use the available Ethernet interface. So we want Jupyter. I guess IPython 3 isn't what I'd need anyway. Oh, Jupyter Notebook. Ooh, I guess this is the new hotness. And then IP equals the IP address that just scrolled off the top of the screen. 10.0.0.86. This should bind somewhere that we can get to it from our Mac. See, Robert keeps doing this thing where he tries to suggest ways to hate something that I actually like. This is just, like, not a useful thing. Okay, let's actually copy the correct line of text. That's better. Jupyter. Cool. All right, so we've been here before, but just for a quick overview. At first, this just looks kind of like your average kind of mediocre content management system with like a file browser and a way to edit Python. The editor seems all right, but wasn't really what I wanted. But if you go back out to the file browser and we find gimbal paramspace.ipynotebook. Now we've got a bunch of interactive awesomeness in the browser. So each of these little blocks is a chunk of interactive Python code, and you can just run this on the Raspberry Pi with Shift-Enter, and the results stay here in this tidy little notebook for you. So I've been finding this interesting. You can see that this is pretty simple, and we could easily just take some of this and turn it into a standalone Python script when we get what we want. This thing starts a background process, really two background threads that handle reading and writing reading and writing packets to the gimbal. it doesn't give us a whole lot of info about its status. So one thing we might want is to have a method we can call that will wait until the gimbal is connected with a timeout. That could be useful for writing scripts with this. The other thing is we've got this getParam_list, which I think we should just remove. It's kind of a clumsy wrapper around the callback-based getParam, and I think this should just become unnecessary because getParam should become blocking. Because ain't nobody got the patience to do callback-based Python for something like this. And you can see, like, for setParam, I wasn't bothering with callbacks because I could just queue everything in the output buffer, which is probably all right. Unless I'm wary about doing more of this though, because one possibility for what broke the parameters in the original gimbal was a buffer overflow. So I want to be pretty careful about sending too many commands or too long of a command. So I think that's where we should go. We should just improve this FY_proto module a little bit, and then use that to slurp the parameters from gimbal to gimbal. Where did that go? Make sure my SSH connection is still going. I think it must have. Yeah. Did that automatically reconnect? Because I don't think I reconnected the SSHFS. That's neat. Alright, FY_proto. So just for a brief tour of this thing, we've worked on this in a couple of previous streams, but this is the FY_proto gimbal, or proto module. It's got a class in it called gimbal_port, which is the kind of high-level way of talking to the gimbal. It's also got the actual protocol decoder bits that we made originally. It's got a Python representation of one packet. So you can create a packet, you can encode it to a string, it has a useful repr. There's a packet receiver state machine where you can just give it blocks of bytes and then packets come out. And then these are threads that actually are used for the implementation of gimbal_port, and then gimbal_port is mostly what we're going to be hacking on now. I guess the first thing I'm thinking about is, what do I want to change the kind of response? Like, I guess what I would call it is, how do I match up responses to the commands that issued them? Here I was using kind of a FIFO queue, which seemed to be not the right way to do it, and it was also specific to parameters. I mean, it was totally just a hack to try to do one thing, and it didn't end up working very well. So I do want to know what their intended mechanism is for matching up commands and responses. And so one thing I could do is just, if there's something coming in and I know it's a response, then I just pass it off to like a response queue. And the response queue, like when I say queue, what I really mean is a single entry queue. So if there's already something in it when you push a new item in, then I would think that would be an error, but I'd have to think about what kind of error, because that would mean that the device is just sending spurious responses that you haven't asked for. So maybe it's just, print and then leave. But what would usually happen is, I guess now I'm wondering whether to make this pull or push. Do I? Well, let's see. Anyway, I'm getting a little too deep into this. My first question actually is, can I reliably identify, given a single packet, is this a response or not? I think the answer might be yes, because I think responses always have target set to 3. So let's maybe take a look at some of the data we've captured to see if that makes sense. So I think if we search for t equals 3, we'll see just the responses. That was a response to the write settings command. And that's sent by any of the microcontrollers. Cool. So this command 5 was a response to saving settings to flash memory, which is probably a problem when I ran it, since this is not something I want to issue unless I know the settings are good. Oh, nice. This is not a response, but this is the... So this is an example of like an unsolicited command or packet that we're getting to t equals 3. But yeah, that is not actually a response. So command B is kind of special. I think the way I want to organize this is that, first of all, most commands, or most packets targeted at T3 go through the same response system, but maybe commands like B become kind of a special case of a command that looks like that with the T3, but actually needs, needs to have an action that's separate from that response queue. Huh, here's another T3 command 1. Interesting. This is, oh, this is something we sent, so this is probably weird. Right, 1, 2, 3, 4, 5. Yeah. So that's fine. This was from a test where we were sending this command 1 on this serial bus, FY gimbal 1, to see if it would show up in a different form later on this other serial bus, FY gimbal 2. And I think it does, yeah, here it is, with T3. But that's fine, that doesn't actually teach us anything, because we wrote that. Okay, I think I've got a plan for this next part. I was just laughing at Robert's comment that they need to stop doing weird things, because I would usually think the opposite. Like, keep doing weird things, just don't, like, when you do weird things and then like complain that the things that other people are doing don't support it, then I don't know, the other person just doesn't really have any reason to listen. But doing weird things and then learning how to fix it yourself is a pretty good way to learn how those things work. So maybe keep doing weird things, just don't necessarily complain as much. So, just to talk you through my thinking here, I think the first thing I'm imagining trying here is a single entry queue, kind of like what we have right now for parameters, but imagine generalizing this past parameters. So, and imagine not using callbacks. So perhaps this queue actually just has a packet instance in it. So when we get a packet, also, how is that any different from maybe everything needs to be command type specific. So this is the function that gets called. This gets called on the background receive thread, just anytime any packet comes in. I mean, one way that this could work is that any packets that need a response immediately get handled here, and then everything else gets stowed in a queue. And that queue, I think that queue wouldn't necessarily have to have bounded size, but then it would be processed by a loop on the main thread that just extracts packets from that until it gets the one that it's looking for. I mean, part of what this boils down to is if I get a bunch of spurious packets in on the serial port, who do I want to be responsible for disposing of them? Where would be the kind of easiest debug situation? And yeah, I think what I like is, because there's also this logging. One option would be to do kind of maximally verbose logging and log everything that comes in. Which I think I kind of want to do at this point. Let's maybe log everything. So let's just have low-level logging, and then above this we could maybe discard packets. All right, so we're maybe I should save that. Maybe do something like that to save kind of the raw data and cook it a little bit. And this doesn't really need any more work. So this is the exchange that we make right at the beginning. This is where we might want to wake up the main thread if it's blocking. Does Python, I'm going to have to remember which threading primitives Python likes. Do they have condition variables? Okay, so you can give it an external lock, or it can just make a new lock. That's handy. I'm not really so fussed about having a separate lock for this because it's just a Boolean. Yeah, let's try this. Oh, that's what the width was doing. That is the lock. So this is something new in Python. I'm forgetting what it's called, but yeah, the context management protocol. So that's a general way in Python to have some object that you can maintain, you know, kind of have its own little scope. So like the same way you might have seen, you know, like little objects in the local scope in C++ that just exist to collect a lock. This is kind of the cleaner Python solution for that. So I assume notify also needs, yeah, with CV, self.connected, self.connection state condition. I think that is better. Yeah, so let's have something that waits for a connection. Ah, nice. This is what I was wondering, if there was a nice way to keep track of the timeout dwindling if you wake up and then the condition you're waiting for hasn't occurred yet. This is new in Python 3.2. Is this also called with the lock held? Yeah. seems easy enough. Kate Temkin is failing to understand the point of sandwich. I feel like sandwiches are pretty awesome. I could use a sandwich. I think my usual sandwich spot is not open at this hour. Okay, so we can wait for the connection. We can notify the connection. There's a few other things we need. So this is kind of wrong thinking. This is looking to handle something special because it's a parameter coming back. But I think there should be a queue that goes into, well, I guess we were debating about whether or not that queue should hold only t equals 3 packets. I think maybe it should hold all packets. It's probably safer if it only hold t equals 3 packets. But definitely not either of these going here. Not that. Let's do this. Let's only store the short form packets, which are going to be the interesting ones. Then I don't have to keep track of the framing type up here. So these are only going to be in the smaller protocol and the ones that direct toward what we think is the kind of initiating computer thing. I think here I should just have a command number. Alright, so how do cumulative timeouts work in queues? Because if I wake up and get the wrong packet, I need to know how to get back and reset the timeout. Excuse me, I might just have to keep track of that myself. Do we have time? We need the time module. Something like that. Does that actually work? that's what I want. So the timeout is optional, but if we do have a timeout, we convert it to an absolute deadline. And then we'll need to convert that back into a timeout every time we're about to call this. Oh, Tuco's still napping up there. Something like that. I wonder what happens if you call that with a negative timeout. Ha, I guess I have to clamp that myself. Oh, that's a built-in. Right, this isn't JavaScript. All right. Let's make a little exception for this so it's easy to catch. Yeah, so we're converting that back to a timeout. This should really be packet, not item. Something like that. Okay, I think that's the infrastructure we need, and now we're getting into just cleaning up the higher level stuff a little bit. Save params. This is a dangerous function. Let's make target required. And get param list. I should change that. Get param. This was just a response here. Actually, I think we had code for that I deleted, so we can take a look at that. Yeah. Right, I was treating these as signed integers. I don't know for sure that these are all signed integers. Maybe I should make the format settable up here. Value, target, format. I'm just debating whether to use a dictionary or a list here. I think I'll just use a list. And assume the parameters are just a contiguous block in the first 128, since that's what it seems like so far. So I think with all that, we should be able to write a program that just dumps parameters from each of the microcontrollers in sequence. Program dump. So this time we can start out doing kind of the same procedure. You'll want this program to run before the gimbal's powered up so that it has a chance to start up in serial mode. . 'Cause 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 does this do at timeout? This isn't clear that wait for also has a return value. It would also be useful to have a default timeout appear. Oh, let's just do this. Allow that to over, or no, the other way around. So you can have local overrides, but the default is in the current class. I don't know if this even makes sense, because I think I'd rather just make that part of this program. Maybe I'll keep that decimal. Oh, I have my headphones handy. I'm a little worried about the copyright bot picking up that music, Zach. Do you want to borrow these? Okay. Okay. Ooh. Sorry for the brief distraction. Let's try this. Let's just make sure that it doesn't have any syntax errors, and then we'll try running it on the gimbal that's already got problems. Oh, of course. All the newbie Python 3 mistakes. Okay, so that's waiting for the gimbal to connect for 10 seconds. That's supposed to be 10 seconds. That seemed a little short. It's like 2 seconds. Oh, I mean, I asked it to wait for 2 seconds right there. Where am I getting 10 seconds? And param dump, wait connect. Why isn't that overriding? Oh, that would be why. Let's try that again. All right. Let's try the gimbal. So, I'm gonna double check my wiring, and then the way this will work is I run the script, and then pretty quickly afterwards turn on the power. And maybe hold the gimbal just in case it decides to go flying. All right, 12 volts DC. Let's run the script. Well, that made some progress. Fixing that error right behind there. I think that did the thing. It was pretty noisy, so we should get this to save it in a more compact format, maybe? Oh, it's also mostly scrolled off on account of screen. Let's leave that be and run this in a separate screen. So now we've got a situation just like the Windows software where if we just run this, it doesn't know the gimbal is already in serial mode. So it won't continue until we restart the gimbal, which is a little inconvenient. We could fix it, but we're already basically at parity with the manufacturer software. Didn't take much. All right, what did we just get then? So here's a bunch of t equals 2. Equals 1. These are 128 registers, so a total of 256 bytes for each of the 3 microcontrollers. just saw a bit of a gap in this where it was maybe paused, but I don't see any timeouts. Let's try saving the output this time. Right, reset this. Whoa. Okay, so this is probably more verbose than it needs to be, but we could basically just diff these between the good gimbal and the problematic gimbal. And we could cook it more, but I'd really rather not cook it too much because I think I might burn it. Or rather, I might translate this into data that's harder to deal with rather than easier. I don't know, actually it might be useful to group these first by number and then by axis and print it out that way. Well, I think my goal for this tool is going to be to have mostly just like a log spew of text like this, but then to also print out something that's like a Python data structure I can copy and paste later. So I think that's the data structure I want. Oh, that's not what I wanted. Right. That's how Python works. If you didn't catch what's going on, I ended up making an array with 128 copies of a reference to the same 3-entry array. Which is not what I wanted. That will do something better. That's more intelligible. You think this value might be the problem? This is making it a little easier to see the differences. So just to recap what this format is, let's get the code that generated it up here. So this outer array is organized from 0 to 128 in the same order that things are stored in memory on each microcontroller, what it looks like. Then this tuple is microcontrollers 0, 1, and 2. So each microcontroller is effectively one of X, Y, and Z in a lot of these values. Some of these we might see change based on the gimbal moving around. That's what we've been observing before. And now that we have full vectors, for example, it might be a little easier. I think it's time to move on and try this on the working gimbal. Let's just make sure we have that. It's looking good. Save that in traces. Okay. Let's get back to the physical world here. Oh yeah, I haven't been super caught up with chat, but it looks like some folks are complaining about the YouTube notification system being broken. Yeah, I've heard a lot of mixed results with that. If anyone has suggestions for alternative notifications that I could send out, then that might be nice. I've already got some Twitter bots, and really anything I can shove into a shell script is pretty easy to add to the streaming setup. Let's adjust that cat camera. And let's unbox a gimbal. So thanks again to Mark WHI who donated this one. Very helpful. I was stuck with not a lot of options on debugging this gimbal without a second gimbal. And I wasn't quite ready to throw in the towel yet, but with an offer like this, let's make a little more space. Alright, here's the shiny mini 3D gimbal. This is overall a pretty nice little product. I'm happy with this gimbal. And it's an interesting design, which would be nice to be able to have a little package of open source software to speak the protocol. So the instructions, so far this looks exactly the same as the previous one, so I think we've got the right model. It's talking about how to attach it to your quadcopter. It's got all the breakouts for yaw, pitch, mode select, video output. You can face it in a couple of different angles. Warranty card. And cool. So we've got a little box on top. And then the actual gimbal is packed in that little configuration there. So, got all these little rubber balls for vibration damping. We've got a little breakout cable, which includes pitch and yaw, mode and ground, 12-volt power, and composite video on those little tiny leads. We've got part of the mounting bracket for a GoPro. And these are more of the pieces to mount this to a quadcopter. So this is the other piece that the little squidgy shock absorber is attached to. And then these attach to, I think, your quad's landing gear or something else like that. Oh yeah, just to recap on where the gimbal lost its parameters. So yeah, as Joseph Hall says in chat, so Joseph says, yeah, she sent some sort of giant version of the get parameter command that might have triggered a buffer overflow or some other firmware bug. Yeah, that's my best guess so far. Since when we saw the video footage of around the time when the gimbal actually lost its parameters, it violently flailed around, but the commands we sent it were just gets, so I think it must have misinterpreted the overly long get command as something else, or it was just a buffer overflow. Yeah, this definitely was something that happened over the serial port, so, I mean, I'm sure there are several ways you can brick a device like this over the serial port. It's not really designed to be secure against that. Alright, so here's the gimbal itself. Might be fun to mount. Well, we should power this on just to make sure it works, and it needs enough mass before it powers on, otherwise it'll just oscillate, so I'll put a GoPro in it. We can use it as it was designed. And what's in the bottom? Oh, cables. So we have, this is the little cable that goes from the end of the gimbal to a GoPro USB plug. So this carries 5-volt power and composite video. I had already taken this apart before you saw the gimbal last time, but I used parts of that in my wiring harness. And then we have some kind of tiny low-quality micro USB cable and a USB to USB adapter, which is actually the serial interface. You might not have seen this with the cover on either, but this is a USB to serial dongle, which I already have one of these taken apart over here, so I probably won't bother taking another one apart. I'll just put that. I might have just now cleaned it up to somewhere that I can't quite find, but anyway, that's not super important. Oh, here it is. Right. Here's the one I already took apart. So there's the USB to USB adapter, and inside it's actually just one of these. If it would ever focus. Scilab's USB chip. So pretty basic. It's just frustrating that they used a USB connector here instead of something a little more appropriate. And that's all she wrote. So I'm going to leave these in the box since we already have the other serial adapter. I'll leave the warranty card and the instructions. So we will need the wiring harness and the GoPro bracket and the gimbal itself. The wiring harness I'll just be using to power it. Alright, I will get a GoPro. There's my venerable GoPro Hero 3. Let's try that. So that just fits right there. It's actually a pretty nice little screw-on mechanism. Let's see if I can get that on video a little better. Apparently there was some grease on one of those parts that I just put my finger through. It's fine. Speaking of the scanlime signal from chat, I should just do my own version of the bay lights, clearly. It would be sad if it was that easy to induce a buffer overflow in the gimbal software. Although, you know, we probably don't need to see the gimbal firmware binary, but it would be really interesting. So that's interesting. This gimbal was sold on a website that included a photo that did not include the silkscreen. So that was something that concerned me. Like, I wasn't sure if I was getting exactly the same gimbal version that I already have. But I think the website was using the box art, and the box art actually does not include this. And in the box art, some of the aluminum parts look like they're actually plastic. So, yeah, see? So if you're trying to find one of these gimbals to play along, if you see a photo where it looks like the covers on the motor housings are plastic, it's probably just a copy of this box art, which is probably like a pre-production model. But the closest version that they have, which isn't this, is the Feiyu Mini 3D Pro. And I think the main difference between the Pro and this, as far as what I've seen in the photos so far, is that on the Pro, it looks like there's an upper aluminum housing that covers the connectors here, whereas on the non-Pro model, this is just a circuit board. So I think that's maybe that's at least a hint that I seemed to have some luck with. So you can see, you know, it kind of balances. It's not perfectly balanced, but it's close. It's definitely not optically centered, but that's just the design choice they made. So then, oops. I would like to stick this on a vise to stabilize it, maybe. We could just try replacing this on the vise. Oh, you know what? I could even just use this wiring harness as is, since there's no reason to rewire it. Let's put the wiring harness back for now. Okay, so this is the setup we were just using. Raspberry Pi is still powered on and running. At least it should be. Yeah, Raspberry Pi is still happy. It is connected through these connections to pitch and yaw, which are actually being the serial port. I've also got this little debug header down here, which I'm going to try to carefully dislodge. As fun as this debug header is, I might take it off shortly after unsaddening this gimbal, since I kind of want to use this gimbal in my cat robot, and the SWD header is not super helpful for that. We've looked a little bit at the SWD. It has flash readout protection enabled on the STM32 processor, which seems to mean that once the debugger attaches, it disables flash access. Because we couldn't single step, we couldn't read flash. You can read and write SRAM, but it doesn't seem like you can cause the processor to make progress. So at least I didn't have any luck with like single stepping or changing the program counter. All right, debug header. Now this just needs to come out. Okay. Great, so there's the sad gimbal. Looking physically pretty good, but firmware-wise, it's kind of sad. Here's the brand new gimbal. All of this wiring should be pretty verified already. The first thing I want to do is just try this normally, so not talk on the serial port at all. Let's make sure that my program is not running. And then just turn this on and watch it hold steady. So I'm just going to restart the Jupyter kernel to make sure that's not running anything. I don't think we even started anything in Jupyter, but just to be on the safe side. None of my scripts are running. So it's ready to run, but isn't running yet. Okay, can we focus? All right, well, here goes nothing. Just powering on the gimbal. Defaults, no inputs. That seems like a happy gimbal. So no input, but it's already just stabilizing and following the heading. Huh. You know, this one's also centered pointing forward, which is not something you could say about my other gimbal. It had locked itself into a center that was pointing pretty far down. So that's also something I might want to know how to tweak myself. Oh, that's cool. It's nice to hear from Mike Matisse in the chat that they like the reminders that I'm still streaming from the Twitter bot. Yeah, I was trying to make sure that those didn't cross the boundary to being annoying. I think the screenshot helps them stay relevant. So, this little guy's happy. Let's try to run this with our script and suck up the parameters now. Okay, so I'm going to run this after turning the gimbal off and just before turning it back on. Oh, yeah, Mike says it's funny when the reminders pop up when you're trying to shut it down and then you go for another hour or two. Yeah, I find that funny too. Let's kill that window and just go for this. All right, power off. All right, I think we just did it. Let's power it off again and take a look at what we got. Nice. Ryan says, hopefully like Servo FY gimbal doesn't take on a second meaning as FY gimbal. Yes. I guess it could. I guess where the FY came from is I was kind of copying the naming convention that they seem to use for some of the like Windows tools. But yeah, I guess that could definitely make sense. What do we have? And what mouse do I need to use to explore it? Oh, interesting. So this was not an aberration. I thought that third number being so weird for index 0 was unusual, but... So one thing we are seeing now is any difference between the axes. So these triples are microcontrollers number 0, 1, and 2, which I think correspond to the yaw, roll, and pitch axes, respectively. But then my hunch is also that the third microcontroller here is also the one doing the kind of overall orchestration. So that might explain why it has kind of different numbers for some of these. These also might just be related to how it's mounted or how it's currently positioned. I wonder if these are gains that are scaled by some amount, or whether these are actually like 0 in some kind of offset notation. I'm just thinking about like what I might have skipped in trying to reset the parameters to all zeros to get the gimbal to at least be quiet, because that just made it really not quiet. Oh, I'm tempted to check these in before I do anything else so I just don't lose them. All right, so we've checked that in. This is way too wide. I mean, I think we should probably just try splatting these all on and then saving them while the gimbal control loop is off. Well, let's try something else. Before I unhook this gimbal, let's just try taking multiple param traces. So I'm just going to try running this in a couple of different gimbal orientations, maybe. Maybe I'll even try to do some where I hold the axes at their extremes. So here's one with all the axes going one direction. And something like that. Whoa. Oh, good idea. Sodium points out I might get some interesting data if I mount the gimbal pointing up. Yeah. Yeah, the manual did specifically call out a couple of different... Whoa. That started to move, which isn't what I wanted. Okay. Sodium points out 16384 is exactly 2 to the 14. Yeah. Yeah, the reason that was interesting to me is it seemed like being a round binary number like that, it was likely either to be an offset, like this is 0, or a scale, like this is 1, or something related to those numbers. So I guess the step I skipped was assuming that these are going to be fixed point numbers. So I'm assuming that they're physical quantities or sensor values that are represented with, you know, like imagine they're floating point numbers, but they're pre-multiplied by something and then rounded to the nearest integer, and that's how they're stored. So maybe I will run the gimbal once up in this orientation just to have it adjust for that orientation in case there's something that it writes to memory. And then try this with the Python program again. I think that this is backwards, actually. Oh, I turned on the GoPro. I think that's the way it wants to be. Yeah, so I guess the software would have to know specifically like what orientation that elbow joint is in. It does change. Oh, gotcha. Sliding it in here pushes the power button. Let's try the experiment. Oh, don't stop automatically. That's cute. It's really nice. I mean, I like the way it looks kind of sticking up like that. It kind of makes me want to build like a turtle robot or something. All right, so then... All right, maybe front. I think I'm about ready to try stuffing these parameters in the other gimbal. Unless anyone else can think of tests that I should run with this one right away, but it's pretty easy to switch between these. As I rotate the shoulder to the other side. Okay, one more of these, and then I think I'm switching gimbals. Oh, I would love some noodles. I can wrap up this stream and get some dinner in a sec. Whoa, Zach made noodles. Okay, I think that's the last of what we needed. Man, splat params just sound super dangerous. Maybe that'll be better. Yeah. Power's off. Gimbal unplugged. When these gimbals are just sitting on the table, they kind of look like sleeping giants or something. Just like joints are kind of all curled up. I guess that's an okay way to sit them. Or it would be if I hadn't put a heatsink right there. Oh, thank you so much. Whoa. I should eat something. Oh man, well, maybe I should wrap this up soon and actually have a chance to enjoy this. This is really good. Let's see if we can quickly splat some parameters onto this gimbal before we call it a night. Because I'm kind of curious if we can fix this. Oops, looks like chat got stuck. Oh, I guess that's just where it is. Whoops. Oh, Noodle Feet. Yes, that's a great robot. Yes, definitely check out Sarah's channel, or you might have seen her work, but if you haven't, like, it's pretty awesome. She's got a robot called Noodle Feet. Some really cute videos of it noodling around. There we go, refresh folders. I always forget where that menu item is in here. Now we've got all this stuff. Dangerously splat params is where we're headed. So the idea with this, we want to connect, then I think we just want to set a bunch of parameters, write it to EEPROM. I guess the write command needs to actually wait for the response. So we have save params for a particular target. This is what tells the gimbal to copy parameters from RAM into non-volatile memory. So I think the flow here is we'll install the parameters into RAM, we'll save them, disconnect everything, and then just let the gimbal start itself up. Because I don't really trust myself to start up the gimbal from the mode where it's just sitting in the serial, interaction mode yet. That's code I haven't written yet, and that actually involves writing to the parameter space, so I don't want to do that in combination with like saving. I want the saving to be done while the gimbal's off. So yeah, I think I send the params, I save them, I get the response from saving them, and then I'm done. Then I just power it off and I restart the gimbal normally. Something similar. This is doing a wait response. Band 5. This gets a 1 byte packet that should just indicate what the target was. So I think I'm just going to test that, and if it doesn't match, then we can raise an error. So we'll check to see if the packet's what we want. If it isn't, then we'll just log this error and go away. So first of all, let's try saving without actually changing anything, just to see if that part works. Let's just see if we can do that as a baseline. Just try to save the params without changing them. We know that this is safe because we've seen the Windows app do this to change the heading. It just changes the param it's interested in, then saves them all. I don't think anything special is necessary in that case. Or if the special stuff is necessary, it's already done in firmware. So dangerously splat. For this, we'll need that same connector plugged back in, and we'll leave the other stuff. So this one has some non-standard connectors. It has SDI video, and it has is that in? No, it's in. It has SDI video, and it has this debug/internal communications header that we've broken out on the back. Alright, dangerously splat. Can we do it? Cool. That looks like what we want. So we get TX 0, 1. Great. And so for each one, after the save is complete, you can see it responds with its own number in the data field. So for 0, it wasn't exciting. For 1, you can start to see, oh, this is different. And then by here, the pattern is pretty clear. So I think that's what we want. Let's try actually changing the parameters. So let's use this fresh params 1 dump, so it's the first one we grabbed. And let's start with this. That'll be the parameter list. Just let it hang out as a super long line, because why not? Target number value. I think that's what I'm going to do. So I'm not turning on the motor drivers. That's a separate command that isn't in the parameter space. Oh, I think we need to give it some time. I think we were exceeding its queuing capacity there. Is there like a ping command we can use to test the back and forth? We could issue another get, maybe. Dual purpose. So we'll use that as an opportunity just to see what it is right after reading back. We'll also use that to make sure that we don't write too fast and then end up with a timeout later. Let's save this. I think that worked. This will be interesting to look at later. I think right now I'm just going to try turning on the gimbal. Alright, I think this is our moment of truth here. So I'm not running the script anymore on the Raspberry. I'm just going to power cycle the gimbal and hold it and see if it starts acting normally or if it starts thrashing itself. Huh. It was slowly thrashing itself, which is different. It's like bouncing against the yaw axes. Let's just try that again and see if it's the same. I'm gonna still gently hold it this time. It's oscillating in that yaw axis, but the other axes are fine, as far as I can tell. That's definitely an improvement. Let's see what it does if I don't hold it. It seemed like it started off moving pretty slowly. Yeah, the pitch axis and it looks like the roll axis stabilize themselves. It's possible there's something that is a little bit weird about the third axis. Well, so I guess in my theory so far, that's going to be axis 0 causing the problem. Interesting. Now it's tempting. What's tempting? Yeah, I know. I was thinking I should, like, there's more to do, but my noodles are getting cold, and I think this is a good time to wrap up. So I think this is definitely an improvement, and we've got some data to look at. I'm going to go ahead and commit these to GitHub, and if you want to play along at home, you can take a look, but I'll be taking a look at it soon, too. Yeah, I'm gonna eat my noodles. So yeah, just in case you want to play along at home, there's the Git repo scanlime /fy gimbal, which could mean anything you want it to mean, including Feiyu Tech gimbal. But for now, I think this is the end of our stream. Thanks for tuning in, everyone, and I will see you next time. And if you want to keep track of Tuco's antics in the meantime, then you can check out twitch.tv/TucoFlyer. It doesn't fly yet, but we're just testing the streams, and you might see Tuco on there anyway. But eventually, some flying. Oh yeah, that notification sound was when it was added. It's actually much louder than I'd like it to be, but I don't have a... Like, it's kind of just depends on which computer I leave Gitter running on and what its volume happens to be set to. Anyway, see you next time. Ah, still warm.